you probably want to click it and then you can.
Okay. So this is just a really brief outline of what I'm going to talk about. I just want to say a few words about the data and the procedures. I'll spend a little more time on the resolution of the models. And then I want to digress into talking about some work that McKinsey and I have been doing it and trying to relate the seismic models that we have, or the seismic results we have, to laboratory results. And then I'll show a little more about the tomographic models and then talk about the implications. So this is the data that I don't know what the background of most of you are, but this is the data that we have that we're stuck with when we try to work. What we'd like to do is, or what we do is something that's analogous to medical tomography. The difference being that in medical tomography, you know exactly where the receiver is, you know exactly where the source is, you know exactly the timing of the source and things like that, as opposed to seismology, where you have this very uneven distribution of events shown on the red on the left here. And you've got this uneven distribution of stations, which primarily is in continents, where there's a few in the oceans. Most of these are from, most of the data that I've used comes from IRIS, like the guy said. And it consists of events with CMT solutions. So I've taken every single a 2-hour window of a seismogram for every event at IRIS that's got a CMT solution. Not all those are going to contribute to the model, but there are other places like in southern India here, where I've worked with the Indians for about 20 years and have access to their network data. Most of it temporary, I should say. And then the other place is this country right here, Iran, which is another country that's difficult. Neither one of those countries really provides data to the data center. So it makes a little difference in these models. But you can see that there's a very uneven distribution of events. There's an uneven distribution of stations. There's big areas like in Russia, in parts of northern parts of South America and Africa, where there's just no coverage whatsoever. So anyway, this is what we have to work with. And in total, I've looked at something on the order of a little more than 12 million seismograms and inverted those. Not all of those are going to contribute to the model. First of all, some are too small. I mean, they've got CMT solutions. It's not that they're too small, but they're noisy. And so those are thrown out. And also, one of the problems I think with the CMT solution is when you calculate the synthetics for an event, one of the things you need to know is the depth. And the CMT solutions, the depths are problematic. But lots of them are fine. But we've looked at individual ones, and some of those CMT solutions can be off in depth by 40, 50, 80 kilometers, which makes a big difference when you try to calculate synthetics for those events. The procedure that we've used, Carl and Levesque proposed a way to strip information from the seismogram using what they called secondary variables. The secondary variable is just a way of parameterizing something out of the seismogram. I mean, in some sense, dispersion curves are secondary variables. Eric, when he was postdoc at AMU, automated that process. So rather than do it event by hand, he automated it so he could extract the Rayleigh wave propagation characteristics along a path automatically, and he updated that in 2012. So I'll show you an example in a minute of that process. TAC and Eric and I extended this process to loveways. The loveways are a lot more problematic because they're the horizontal components are a lot noisier. You've got to have the two horizontal components working at the same time. And lots of times I think the seismograms are just misaligned. So what's supposed to be pointing north, sometimes it's just off by a small amount. But I believe that in some cases, people have oriented the seismograph, the north on the instrument towards magnetic north, for example, rather than true north. And lots of times, I mean, there's been instruments where we found that north is pointing what should be the northern channel is pointing east, and the east channel is pointing south. There's other problems with the data. So the data that you get from IRIS, really, you need to spend some time examining it for these kind of problems. But anyway, so we extended these procedures to loveways, and now we've extended it to extract radial anisotropy along the path. And for the tomography, so these all are to extract the information for a path, the propagation characteristics, and then we use this procedure by Eric and Malcolm Sandbridge, which is an extension of a tomographic method that Jean-Paul Montagnier proposed in the 1986. So that's all I wanted to show about that. I'll show just one example of how that's done. So you start with, this is an observation. So these are the data, and calculate a synthetic for that. The synthetic is calculated for a model that's like Prem, but it has the 220 discontinuity smoothed out, so we don't have that discontinuity frozen in. And the Prem crust is replaced by a crust extracted from crust one that Guy and Gabby and I worked on. So we calculated a single mode synthetic, the longest periods that come from the noise. The longest period I worked with is 250 seconds, but most of the time 250 seconds is not available. So calculated a single mode synthetic, cross-correlated with the data, and extract the information for the secondary variables, which is this cross-parallelogram or this phase. And start with the lowest frequencies, work up for the fundamental mode. And each time you add another frequency in, you update the model. So you start with a model based on the fundamental mode, and if there's overtone information, then start adding those in, starting from the longest period. And I only go up to the 6th overtone in this for technical reasons. So you start out with something like this. This is the data. This is the initial synthetic, and this is the residual. And through this process, end up with the data again. This is the fit of the final model. This is the unexplained part of the waveform. In looking at the anisotropy, what you need is a good azimuthal coverage. And it's different for Rayleigh waves and loveways. So this is an example of how we assess the information for the Rayleigh waves. Take a 2-degree cell, a geographic cell, and then we'll divide it up into these pie-shaped segments and look to see how many of those segments actually have a path propagating along that azimuth. So, for example, this one has no paths. This one has 2 propagating, one in this direction, one in this direction. And if you don't have sufficient azimuthal coverage in the cell, then combine the cells and make a larger cell. And keep expanding those cells until you get to what's shown at the top there, which would be considered good azimuthal coverage. Doesn't necessarily mean that you can still have a good anisotropic measurement. For the love waves, it's more complicated because the Rayleigh waves that have they have a 2 theta, 4 theta, and so on, azimuthal contribution, but for Rayleigh waves, the 4 theta amplitude is within the noise, so we don't worry about it. The log waves are different. For those, there's a 2 theta azimuthal measurement, there's a 4 theta, and for the log waves, the 2 theta measurement is small and within the noise. So we start, and so now we're looking at a 4 theta pattern, so we need to start with a 9 segment cells and gradually build these cells together until we get good azimuthal coverage, which would be these here. And so if I show what those maps look like, this is a map for the Rayleigh waves. So we divide it up into 2-degree cells here. This underlying blackness and grayness is the number of paths through those particular cells. So you can see that north of about 45-50 degrees south, the coverage is for Rayleigh waves is excellent. So there's approximately 5.5 million waveforms contributing to this. So the only places here really that the resolution is poor is down here in this area off the Cratonic Peninsula. Even down here, where the number of paths is small, something between 250 to 500% per cell, it's still good azimuthal coverage. If you look at the love waves, it's not quite so good. So there's many fewer love waves contributing, whereas there's about over 5 million waveforms for the Rayleigh waves. There's slightly less than 1 million for the love waves. You see north of about 30 degrees south, it's relatively good. There's some places here in the Pacific, South Pacific, where the azimuthal coverage is not so good. In the southern Indian Ocean and all of the Southern Ocean is poor. Not poor, it just means that you can't resolve the anisotropy to any better than an area, this sort of area. And for radial anisotropy, it's worse again, or degraded further. The reason for this is in computing the radial anisotropy, we jointly invert the love waves and the Rayleigh waves. And so we need a good measurement, a good waveform for the love waves and a good waveform for the Rayleigh waves on the same path. And that's even harder to come by. But you see that north of about 20 south or so, the coverage is reasonably good, except down here in southern oceans. And down in the South Polar region, that's poor. So the kind of tomography you're going to do is great circle tomography and use an influence zone about the great circle. So it's not as accurate as using like the spectral element forward calculation, but the advantage is that you can do that they're fast. So I can invert 12 million waveforms on our small cluster that we have in a couple of weeks, rather than, and you couldn't do that with the spectral element methods so far. There's been lots of, or a number of papers that have tried to compare the spectral element results with these less accurate forward calculations. And I just found one here. I know there's some other ones where this group in Japan compared different kinds of forward calculations. So this is just the great circle calculation, which is what I'm using here. This is using with an influence zone, and this one is doing ray tracing with an influence zone. And then the plot on the far right is just the difference between those two. So there's been other studies, Anne Zemansky who was in Strasbourg at the time, looked at calculating or doing the tomography with an accurate forward model calculation like SpecFem, and then doing the great circle approximation. And you could resolve similar structure because there was a trade-off in doing the more accurate, for example, spectral element calculation. It's slow, so you can only do a limited number of wave paths or propagation paths. Whereas with this kind of method, you can use much more data, and there's a trade-off between the data coverage and the accuracy of the forward modeling. So these are the kind of models that produce. This is what the South, the Pacific Hemisphere looks like at 75 kilometers depth. You can see the East Pacific rise here, the back arc basins, the Western United States. There's also this feature here, which is a low velocity zone in the Nazca plate, and this low velocity zone here corresponds to a ridge which jumped from here to here about, I think, something on the order of 12 million years ago. So well, we'll talk about in a minute. This is the thermal signal left from that ridge. These cross sections here, the top one, A prime, beta A prime, goes across the East Pacific rise, across Hawaii into the Japanese Arc. And you can see the low velocities in the upper mantle for Hawaii here. This one, B prime here goes from the Western US to Eastern Australia. You can see the Vanuatu subduction zone, the back arc basin here, and Hawaii again. And then this one is from Central America to across to Tonga. I just show one more picture. This is the Eurasia, Indoeurasion collision zone at 125 kilometers depth. You see the low velocities in the shield from India, low velocities in Asia. This is the Western Siberian Craton. This is the Eastern Eurasian Craton. The Western Siberian Basin, it's a deep sedimentary basin, but it has high velocity upper mantle. The three cross sections here, AA prime goes from off the coast of India to near Mongolia, and you can see the underthrusting of the Indian lithosphere beneath Tibet. This region here is a low velocity region above the high velocity slab, and we think that's a result of additional, the thickened crust here, and that has radiogenic heating, and in that thickened and blanketed crust, it creates a velocity inversion. So the upper mantle actually is being heated by the radiogenic heating from the crust. So now I just want to digress from the seismology a little bit. And this is an old slide. I should have made a new one, but I just ran out of time. This is the Pacific from down to 400 kilometers depth. And this is age. So what I did is I removed the measure. I removed all parts of the Pacific that were anomalous. So it was like around Hawaii, or the Java Plateau, anything like that. So I just looked at the Pacific that was where the plate was forming at the ridge crest, and just forming as it moved off towards Japan. So this is what it looks like. You can see the formation of the high velocity plate there. The slow velocity zone extends out to about 125 million years. And this is a plate model for the temperature that we derived or published in 2005. And so what I did is I took this waveforms here and the temperature there and plotted the velocity versus temperature. This is this is the old part of the plate, is colder, faster. This is getting closer to the ridge crest. And then when you get close to the solidus, there's this very sharp downward hook before the melting takes place. And that same thing has been seen in that same feature has been seen in laboratory experiments in Australia, and on olivine samples, olivine powdered samples. So what they had was something that with the right chemistry, but the wrong crystalline, the wrong particle size. So taking that, and this is something that's we've just done about 10 days ago. So this is the new models for the Pacific at 40 to 100 kilometers depth. The dots up there are temperature and velocity measurements from mostly peridotite nodules. And then this curve here is an estimate of the temperature and velocity from the convecting part of the Pacific. This plot on the other side here is just a blow up of this section here. There's the red curves, the smooth curves that I'll talk about just in a second. These ones with kinks are the observations, and this is the melting point. So you see that these curves, this is all the thing, these come down and just touch the melting point curve, and then I don't have any measurements past that. These three here are from across here are fitting, and I'm sure you can't read this. I didn't make this slide. I asked somebody to make it for me, and this is what I got. But these here shows in the weighting for fitting the data. So the weights are the weighted 5 for the seismology and 0.02 for the nodules. So the measurement or the relationship between velocity and temperature you have has information from the nodules, the upper mantle nodules in there, but they're not weighted, they're down weighted. And we've been working with a person, Toshio Kai in Japan, who's using an alcohol to called Borneal as an analog for olivine. And so she's been making the measurements on olivine, on this olivine substitute. And what we've done then is use her laboratory measurements to derive a relationship between temperature and pressure and compare it to the seismology. And then use the relationship from the seismology and compare it to the Borneal measurements. And we've got those to match now. So we can actually take the laboratory measurements and predict what the seismology is. And the seismology and predict what the laboratory measurements are. These plots down here are clicks again. This was not so good, but these are observed minus calculated. This is at 40 kilometers depth, 50 kilometers depth, 70 kilometers depth. The reason for this being off at 90 kilometers depth is that's right at the base of the plate. So it's being affected by the waves of the resolution, the depth resolution there is extending from the seismology is also sampling the azimuthal. This measurement here is for the convecting of the mantle, and it would be improved. And this is the spread in the nodules. So this is the prediction of the nodule velocity, the calculated nodule, the calculated velocity for nodules minus the actual measured value. And so what we've done then is use those measurements to derive maps of what the lithosphere looks like. But this is the thermal lithosphere. So most seismologists, I was just meeting in Toronto, and virtually every seismologist looks at the lithosphere as a high velocity lid over a low velocity upper mantle. But that's not the case. I mean, you can have a lithospheric plate where the velocity just increases with depth, and it just goes from a conducting region to a advecting region. So the way we define a lithosphere is shown in this plot here. These are upper mantle nodules, so they're measurements of the pressure and temperature in from the nodule last equilibrated. So these are the measurements from the nodules, but there's other information in here too. So we know that the surface temperature is about 0, roughly, and we know sort of what the geotherm within the crust should be. This is in old Archean crust. Should be from measurements that people have made. And then we know what this point is here from the thickness of the oceanic crust. So the oceanic crust forms by decompression melting, and the higher the temperature, the more melt it generates. But most of the oceanic crust is on the order of 6 to 7 kilometers. And that gives this potential temperature of the upper mantle of about 13, 15. So in other areas like Iceland, where you have excess temperature, you've got excess melting, so you have a much thicker crust. So Iceland is basically just a very thick section of oceanic crust. And this shows a plot of the measurements, the geotherm based on the nodules, similar to what I just showed a minute ago, but these are all from South Africa. And these measurements here, this geotherm here, is the geotherm was predicted, these dots of the geotherm was predicted by the seismology overlaying on what the geotherm from the mantle nodules is. So the agreement is good at these deeper depths, but it starts to break down at shallower depths. And the reason for that, I think, is that although a lot of effort's been put into deriving a global crustal model, there's undoubtedly regions where there's just no data, and so the crustal models are not quite perfect. For example, I've had a student who just finished his PhD in Iran, and what we did to start with, we wanted to look at the mantle, but what he did first is look at the crust. And so we derived a really detailed crustal model for Iran, and in the places it was off by differed from crust 1 by as much as 10 kilometers. So in what the seismology, the tomography done now is we've used crust 1 as the crustal model for the path, but we've modified crust 1 by putting those other measurements in. So you get a picture that looks like this. So this is the thickness of the lithosphere, thin in the oceans, thinnest around the ridges, thickens as it goes to older ages. And the blue here is where the Archean cratons are. So you get thick lithosphere through Brazil here. This piece here is a lithosphere as a conducting slab, which is also cold. So this is based on the temperature. And so there are things in here like this glass slab. But it's North American craton, West African craton, the Congo craton, Kalahari craton, cratons in Australia, and so on. And you see that the one craton that we haven't got a thick lithosphere is this Sino-Korean craton, and it's got Archean crust. It's got diamonds from the Ordovician, but it has no thick lithosphere for that area. So now I'll come back to the lithosphere model in just a little bit, but now I want to talk a little bit about the anisotropy. And I've just plotted two model, the model here at two depths, 150 kilometers and 250 kilometers. And you can see in most of the oceans, few parts different, that this value here is the ratio of the SH velocity to SV velocity. So if SH is fast, meaning the horizontal propagating waves are faster, it's here in the red. If the vertical propagating waves are faster, it's in the blue. And so through the oceans, almost uniformly, SH is fast with respect to SV at these shallow depths. So this is just below the plate. As you go to deeper depths, the picture changes. And then in particular, this area of the East Pacific rise here shows SV fast rather than SH fast. And the other thing I'll come back to in a few minutes is if you look at the Cratons, they're primarily SV fast over SH fast. What time does this end? At 1. So I got a couple more minutes. Okay.
Sorry, so when you talk about SH and SV here, do you mean vertically traveling and horizontally traveling waves, or horizontally and vertically polarized waves?
Polarized. So it's
Polarized.
radial. The SV fast is what I mean is the Rayleigh wave. PSV motion is faster for where it's red there, the SH motion is faster.
Okay, so it's the polarization of the SH.
Yeah.
Oh, okay.
Yeah. So it comes from love waves, which are primarily SH, and Rayleigh waves, which are PSV. This picture here is, I'm sure, too confusing to mean much at all. But what I wanted to do was plot the azimuthal anisotropy. So this is how the Rayleigh wave changes at a point because of direction. And so these little black sticks show the Rayleigh wave. So Rayleigh wave is fast in this azimuth here, for example. It's fast in this azimuth here. Underneath it, I tried to decimate this to make it clear, but it's not. Underneath it are these crosses, and those are the love wave measurements, polarization measurements. And the two things that you can see in this picture are, one is that the azimuthal anisotropy decreases with depth, and that's been known for a long time. And there's this area in the Pacific where the Rayleigh wave anisotropy is larger and the love wave anisotropy is small. And I don't understand how, if you have, I mean, I'm sure people do, but not me, understand if you have an olivine crystal, you've got the Rayleigh wave propagating in one direction, and I can understand that, but I don't quite understand its relationship to the love wave. Not that I don't understand the relationship, it's that I don't understand that picture. Why, for example, in this region here, the Rayleigh waves are fast, but there's almost no love wave signal. Whereas in these regions where there's convergence or divergence, the love wave signals are large. So I don't know what's governing the amplitude of those signals. This picture shows the radial anisotropy again now for the oceans. So the Atlantic and the Indian Ocean are slow spreading oceans. And this radial anisotropy, I've binned it in these 5 different bins. The reason I chose those times periods was because there was a really important paper published in 1989, and they binned the anisotropy in the same way. No, they binned the velocities in the same way. So in the Atlantic Ocean, the Pacific, and the Indian Ocean, the anisotropy close to the ridge crest is the same as the anisotropy at large distances from the ridge crest. The Pacific is different. Older parts of the Pacific look just like over these 2 slower spreading oceans. But up till 20 million years, it has a different structure in the anisotropy. So I took out the southern Pacific Ocean, which is slower spreading than the farther north of the East Pacific rise. And this slower part of the ocean looks more like the slower part of the Pacific, I think, looks more similar to these slower parts in the Indian Ocean and the Atlantic Ocean. These two pictures are just maps of the azimuthal anisotropy, and you see over the Pacific. I probably contoured this at a value much too close, so that's 1.07, that's 1.6. So I need to redo that. But anyway, most of the Pacific at this depth, 9 kilometers. So this is in the base of the plate for the older parts of the ocean, but not for near the ridge. This is horizontal motion. If you go below the plate, it's different for the South Pacific here from the north of 25 north. So this very southern part of the Pacific at least looks to me to be somewhat different from this region to the north. And that's also been seen by the French. And one of the things they proposed was this is the formation of a new plate boundary. But this difference in anisotropy actually occurs below the plate. At least I don't see it at these shallower depths, but it doesn't mix up here. As you go to deeper depths, then the anisotropy changes. So SV is fast, especially in the region of the East Pacific rise. So I'm just going to talk about some how we try to interpret this. And most of the mantle, the upper mantle is olivine. There's orthoparacines and finoparacines too, but something like 75 to 80% of the upper mantle is olivine. We'll just assume that it's going to be an olivine mantle, and these are the velocity crystal. Velocities along the crystal axis. And we'll look at two models, and I realize I forgot something on this slide too. So this upper one here is the Rayleigh wave, the PSV motion, and this is the SH motion. And you see that this has an axis here, where this has the two axes here. There's actually fourth theta motion amplitude here too, but it's small above and below what we can measure seismically. So we'll look at two models. One where the top moves over the bottom, and that gives these values here, and if it's just pure olivine, this value chi, which is s square of SV over square of SH, comes to 1.19, so it's above 1. In this case here, where there's compression, so this is simple shear, this is pure shear, so this is shortening. This is the Rayleigh wave or the P wave, NSP, SV anisotropy for this case, and this is the SH anisotropy. For this, you get a value less than 1. Now, people have used or have tried to use anisotropy to explain deformation in the mantle now for 10, 15 years. People like Thorsten Becker and that. But the one thing with anisotropy is it does have a memory, so that if you have something like this SH over, the top over the bottom, so simple shear, you start with a crystal that looks like this, and as it goes through this process, it's stretched out to look like this. It's not. It also has its memory. So as it has the memory of both the changing from circular shape here to oval shape here, but it also has the bending. So that's for simple shear. For pure shear, you get the same distortion of the crystalline structure, but you don't get this bending shape. So this would be similar to the spreading or the deformation in the Central Pacific. And this is a plot of just the northern part of the Pacific. These purple things are the plate boundaries. So this is the Marianas, this is Japan here, Western North America here. And this is an extraneous line that I got in somehow and I didn't notice. But it was too late. But you can see in this region here, this deformation here's the what I just showed in the previous slide. So this is the Rayleigh wave deformation. And love wave, Rayleigh wave anisotropy. This is shown with the black stick, and the cross shows the love wave anisotropy. And they do agree. So this makes sense. When you get to the central part of the Pacific, the anisotropy gets very small, and then it grows, especially the fourth beta love wave anisotropy as you get to the trench. Now, part of this could be the fact that we no longer have a simple top over bottom, but as you go to the subduction zone, it could be coupling between Rayleigh, above Rayleigh coupling, something like that. So that might explain what's going on here, but at least in the Central Pacific, the pattern is simple. It's just why there's this region, it's low wave speed. I just show the next kind of quickly. This is the anisotropic pattern again. Red is the love waves, black is the Rayleigh waves. This is the tomography permeatic subduction zone. And you see as it comes up to the subduction zone, you get this wrapping around the northern end of the subduction zone. This plot, which is, I tried to make it better, but this is Australia. Australia is moving north at about 5 to 6 centimeters per year. It's moving very fast. And this is the Antarctic plate here. This is the ridge crest between the Antarctica and Australia. And again, I don't understand what's happening here. It does look like in the Cratonic areas here, the anisotropy is wrapping around. But why is this huge signal here? Antarctica is stationary. The ridge and the Australia are moving to the north, but you still get this strong anisotropy in the Arctic plate. And these two plots just show this is a calculation of what the anisotropy would. This is a vertical plate flows in this direction. And this shows how the flow pattern goes around this plate. So it's an idealized subduction zone. And as you get away from it, you get this distorted pattern memory from the northern plate. This is a case for Australia. It's Antarctica, Australia. There's a strong anisotropy here. This is the lithosphere that we get for Australia. This is Antarctica. And so it does look like you might imagine that the anisotropy is being influenced by this plate. But once you get up into the area to the north of Australia, it's just far too complicated. This shows the flow around something like a circular obstacle. So I just want to finish up by showing a couple pictures here. This is lithospheric thickness. This is radial anisotropy. And there's a reasonable visual correlation between areas of thick lithosphere and areas where SV is fast as opposed to SH. So these are Archean Cratons. This is the Indian Eurasian collision zone. So there's this correlation between, this is the isotropic VS, this is the radial anisotropy, this is the lithospheric thickness for North America. That's the best resolved continent, or best resolved of these areas we have. And this is for Antarctica, which is the worst resolved. So again, there is a relation, there appears to be a relationship between the radial anisotropy and the lithospheric thickness. And this is the last slide, which drew to try to explain that. And I realized just this morning, this is all supposed to be Patrick Green here. I still haven't learned Inkscape completely. So what happens is we know that the Cratonic roots are depleted. There are Hartspadites. They've been depleted by a large amount of volcanism, 20% or more volcanism. And there's two things you know about the volcanism is that you couldn't get that amount of volcanism, but the nodules that we have come from these deep depths now. You couldn't get that amount of volcanism at those deep depths because of the higher pressure. So you need much higher temperatures, which may have existed in the Archean, but there's no evidence really that there's that much difference in temperatures in the Archean now. The other thing is that the nodules have this chrome signature, and that chrome signature can only have come from the extraction of the melt in the spinel where spinel is stable. So it had to be above about 85, 90 kilometers. So I think this is what the lithosphere looked like for say North America in the Archean. There was this removal, depletion of the root at shallow depths, and then there was this compressional event, so it shortened by about a factor of 2, taking the root down to these deeper depths, deforming the anisotropy, so we got SD fast rather than SH fast. These aren't quite to scale here. It would also get an uplift, so this might be something like Tibet today. And then with time, once the compressional event stopped, the top would be eroded, this would shallow a bit, but you retain this anisotropic signature in the mantle, in this Archean, the root. So those are just the things that I've talked about, this the temperature relationship, the model for 2 theta, 4 theta azimuthal anisotropy and the radial anisotropy. The radial anisotropy for most of the oceans, except for the young Pacific, is similar. This 2 theta and 4 theta azimuthal anisotropy could provide some information on deformation and mantle, but it's not that straightforward. And finally, the stable cores of the continents have this distinctly positive, not positive, that word shouldn't be there. They have this distinctive psi character centered at about 150 kilometers, which may reflect the initial formation of the cratons. Okay, thank you very much.
Okay, thank you, Case, for the talk. Now let's take questions for the students in the conference room. Questions from everyone, including those on YouTube. You can, for people on Zoom, you can just unmute yourself or put your question in the chat. Go ahead.
So, very nice talk. Can you clarify what the conceit structure means here? Do you mean the transition from positive radial anisotropy to negative radial anisotropy at about 180 kilometers back?
Was that in what in this slide?
The last slide, or so yeah, I didn't quite get what's the. Well, for example, your slide comparing the radial anisotropy with the lithosphere thickness. For example, this one, what do you mean by radial anisotropy here? Is that the average radial anisotropy in a
This
sphere?
is all plotted at 150 kilometers. Well, no, this is at 150 kilometers. This is the velocity. This is the base of this is the radial anisotropy at 150 kilometers depth. So above that, it's red over, and so it goes from red to blue and back to red. So there's a region where SH is fast, it rotates to SV fast, rotates back to SH fast. And this SV path segment is just in the region where you have this thick mantle lithosphere.
I see. So the layer with the negative radial anisotropy only exists below wavelengths.
Yeah, it exists in the Cratonic root. And if you go back to,
So that root exists within the high velocity.
yeah, the root is the high velocity. It's the depleted part of the mantle, and it's viscous, so it deforms, but it's buoyant, so it doesn't gravitationally delaminate.
Mm-hmm.
So you can take them as these continents collide or split up. So one of the things we did is we took this picture, and one of my co-authors used to do plate reconstruction, so he modified his code so he could take the lithosphere and move that backward. And if you do that back to Pangea, it just all fits together. So it must be that when Pangea was formed, since it fits together, it was undoubtedly, it wouldn't just be that way by chance. So it probably deformed to fit together. And then once it's broke up. And even if you look at this region down here, where there's thick lithosphere, there's diamonds off the eastern, western side of the Capel Craton, diamond pipes. They're at where the lithosphere is shallower today than it's above the diamond transition zone. So what must have happened is that it was thick, and then as it stretched to form the Southern Atlantic, it kind of necked out. And certainly this area over here, it's Archean crust, it's got diamonds and Ordovician diamonds, but it doesn't have any mantle root. So they're at high temperature, not as high as a convecting mantle. So they're a very viscous material. So they can deform, but they don't delaminate because they're light. The iron primarily has been removed.
So in other words, you recognize this anisotropic layering within Cratonic lithosphere.
Yeah.
Okay, thanks.
I thought the Korean route had gone because of interaction with the subduction zone. So isn't that a standard way of explaining that?
Yeah, but the people have tried to say, oh, they delaminated it. So it could have been refertilized by the subduction. And so maybe it's there, it's just been refertilized and you don't see it. But it can't be what, like a lot of people say, that it delaminated, because it's light, and it's the light things don't sink into the more dense mantle. So it's probably something to do with this the subduction zone, and also on the surface that whole area has been stretched, so it almost looks like a basin range. So some things, what might have happened is the whole region just got stretched, and so we've just got a thinning of the whole thing. So the lithosphere may be, there may be depleted lithosphere there, but it's now very thin. Don't know. This is the thing.
Here's one chat message. I don't know if somebody is
It's not a question.
okay.
Yeah.
I was wondering, go back to right at the start when you were showing those plots of the azimuthal resolution for different surface waves.
Yeah.
And I was wondering, do you think you could, yeah, these ones, I really like these. And I was wondering, are these telling us where we need to deploy seismic stations and networks in the future.
Yes, it does. And the place that we can really use seismic deployments is in the Southern Ocean, which is a place that's miserable to work. I mean, one of my colleagues just finished an experiment along Macquarie Ridge. And of the 11 instruments, 11 Geralt instruments they put down, lost 6. And, you know, the sea is not nice, flat and calm down there. It's a miserable place to work. So there are stations in like Kirkland and some of these islands, but putting OBS down there is, if you want to lose an instrument, that's where to take it. But yeah, you're right. This tells us where we need more data. And you know, Antarctica doesn't have, it's now got a fair number of temporary stations, data from temporary stations, but there's only I think, as far as I know, there's only one permanent station there. And the other thing I should have said, which I didn't, is I restrict the length of the path, the propagation path. So I only use the minor arc paths, not the major arc paths. And I've gone out to 120 degrees, because if I didn't go that far, I couldn't get anything from the Pacific. I started out just going to 60 degrees, and that left a big hole in the Pacific. So I don't go to longer paths. If you could use longer paths, then you could fill in some of this area here. But because as you go to longer paths, the Rayleigh waves start weaving more, and so the longer the path, the less you know about the path.
More questions? If not, let's then case for the red part.
Thank you for having me. Thanks a lot. I appreciate it.